Good morning, everyone. So I'll be very brief and just introduce Dr. Valerie Fox. So Dr. Fox is a planetary postdoc researcher here at Caltech with Bethany Ehlman's group. She got her PhD from Washington University, I think in 2017, right? She's a specialist in the application of spectral imagers to the study of clay deposits on Mars. And she's led and co-led investigations for the Mars Science Lab and other things at JPL. I think that she's uniquely suited to talk to us about planetary scale questions, data science, and all that. So please give a warm welcome to Dr. Valerie Fox.
Thank you. Yeah, I'm quite excited to be here to talk about, big planets, big questions, and ostensibly big data and what we can do with that in sort of this new and changing paradigm when it comes to data analysis and planetary science. So as Josh said, my background is as a data analysis scientist. I'm a geologist. I think about what the rocks on the ground on Mars are telling us. But in order to have a picture of a rock on the ground on Mars is actually a very complicated process, which should surprise nobody. And planetary science has always existed in a very interesting liminal space. It is, on the one hand, absolutely cutting edge. It's science fiction in terms of the cutting edge technologies, the top-notch people working on it, the applications that we are applying. We're putting our very best and our very brightest to go explore entire new worlds. And yet at the same time, we are starved for data. Scientists will devote entire careers to getting a single picture of a single feature on a planet and accept whatever blurry resolution is required to make that have happened. And so I think we're at a sort of a tipping point where it's really nice to now be able to start trying to move from this, we'll take whatever blurry image of whatever you can get us, into what can we actually do with data analysis techniques, larger data sets? How do we collect those? How do we acquire them in order to apply really poignant science questions to better understand the entirety of our solar system? So what I'm going to spend the next half hour and change discussing really is why we are bothering to study the solar system, what the major scientific questions that we're trying to answer with our spacecrafts and data gathering instruments, and then what controls the type of data that scientists want to get out. I think that it's important to keep the context in mind as we're thinking about data collection and storage and archiving, in terms of what do we actually want and what do we actually need, and what do we need but don't even think to ask for because it's been out of the scope of capability for so long. And then also, I'd like to discuss a little bit about how we are currently doing this. So again, I'm a scientist, so I'm going to give you a little basics on remote sensing through the solar system. Again, that's the context for why and how we want the types of data that we want. And what are the really big data sets, what don't cost very much. And then how do we currently prioritize and select and target our observations? So how are missions working at the moment? And again, trying to spark this idea of how do we change these paradigms to move forward into not a data-starved system. So in terms of the big pictures, about every 10 years, the scientific community gets together in space sciences generally and discusses what are the big types of questions that we think are what is really driving solar system exploration. This is from a planetary science perspective, but they do this for astrophysics, earth sciences, anything space related as well. And for the last decade, it has centered around three major themes. So building new worlds. Fundamentally, how did our solar system come to look the way it is? and why is it, 8 big planets and a whole bunch of little things? Is that standard in the universe? Maybe not. Why? So how did the planets form? What controlled their formation? What controls their composition? Where did the water come from? That seems to be kind of key in our personal existence. And that links into thoughts about planetary habitability. Are we the only planet in this solar system or universe that hosts life? That is kind of a fundamental drive for any reason to be collecting data and exploring beyond our terrestrial borders. And then how do we detect that? How do we define life? How do we measure its presence or its past existence? What sort of signs do we look for when defining something as a habitable environment, whether in the past or the present? And then finally, fundamentally, we want to put all of this together and understand how systems work, how systems in our own Earth, our own planet, relate to systems that are operating on other planets throughout our solar system, operate in other solar systems, and how interactions between, the interior of planets, the surfaces of planets, the atmospheres of planets, and then outer space all interplay and relate to one another in order to better understand how things have shaped through time. So how a planet has gone from being a lump of molten rock that smashed together during accretion to what we see in the solar system today. And so as we're answering these questions, you're like, all right, this is what we want to know. And then you have to start thinking about what are the observations that we're going to be making to actually answer them. So for instance, we want to measure what the planets are made out of. It's a pretty fundamental level type investigation. Measure, do they have an atmosphere? What is that atmosphere made out of? What are the processes therein? And then we want to step down a little bit more nuanced, a little bit more detailed. What are the interior structures and the dynamics, and how are these things interplaying? Again, how are, if a molten lava interior, how is that interacting with the surface in terms of the volcanology, in terms of the energy processes on a planet? What are the geologic processes that are active on a planet? Are there oceans and lakes and rivers that are carving mountains down and depositing them into low basins that are then building up stacks of rock through time? And again, how are atmospheres changing over time? How is climate evolving through solar system history? And then again, we want to interpret all of these identifications and conditions to better understand these systems as a whole. And so as we move from basic level observations deeper, that requires more nuanced observations, better resolutions, larger data sets, more targeted data sets, so that instead of we'll take a flyby and take whatever picture of the planet face that we get, then we want to actually be able to go start targeting of hey, we saw this basin that had interesting deposits in it, and we would like to go see what caused the rock to flow downhill, and was there a lake there? And each of these requires a more and more aggressive data collection strategy, as well as a little bit more care in thinking about how we're processing the data and interpreting the results. And so, of course, the first step to any planetary exploration in data acquisition is to actually send a mission. So for the bodies in our solar system, we have been very busy for the last 60 years. There is an inequity in this list. Mars has been the focus of planetary study, certainly for the last decade. A, because it's fascinating, I say as the very biased Mars scientist. But it's also kind of easy, quote unquote, because it's definitely not easy in a lot of ways. But take Mercury, for example. We've got 2 and a on its way mission. Studying Mercury is really hard because it's so close to the sun, And that is a challenge for two reasons. One, it's very hot, and so you have to build your electronics to survive pretty significant thermal cycles. And then also the sun yanks on your spacecraft, so it's really hard to keep in orbit. So you need to send more and more propellant in order to keep adjusting your spacecraft's trajectory. And therefore, missions to Mercury are not necessarily very long-lived and have significant constraints in terms of their orbital dynamics, which then limits parts of the planet that you can target and the resolutions you can acquire. We look out at the outer solar system. We have two ice giants, massive planets in our solar system, and they have each gotten a single flyby by Voyager 2 30 years ago. And so that right there is going to, this is where we're talking about we're data starved. There are fundamental questions that we would really like to answer. And if we can figure out how to get, an equivalent amount of data as, even, let's say, Magellan at Venus acquired out at Triton, which is Neptune's moon, that would revolutionize our understanding of outer planet dynamics, how our solar system formed overall. And so, like I said, step one, we've got to send a mission. But step two really is you have to know how to send the data back. You have to know how to acquire the data. And so that is what I'm really excited to sort of start digging into during the workshop this week. So like I said, every bit counts. So our exploration of Pluto with the New Horizons mission is an excellent example of how a little bit of data can really fundamentally change our conception of a huge portion of our solar system. So in 2012, we had our best resolved images of Pluto. During the flyby in July 2015, the whole thing lasted a handful of hours. We were able to collect these very high resolution images that showed Pluto not as just a frozen ball of ice stuck out at the end of the solar system, but a very active geological world. So I actually don't really care if Pluto is a planet or not, but it sure is interesting. And this is Alan Stern, the PI. Every time we get a new data product back, like that really is the level of excitement. Certainly heightened for something like Pluto that is so hard to study, takes 10 years to get there. But really every day when we get a new image down from the Mars rover that has driven up over a hill and we see another vista, like we are fundamentally discovering brand new things about our world, and that's really exciting. And so, with 6.25 gigabytes of data, we are learning a lot. And so able to pull information out of every single bit that we can get, and then what could we do with 10 times that amount is a really exciting type of question. And so for some context, in terms of the quantities that missions tend to collect in our current schema. So 3 missions here, for example. The Mars Reconnaissance Orbiter really is a powerhouse mission. It's been operating for the last 13 years around Mars. It has some of the most detailed and data-heavy instrumentation of pretty much any mission that we have sent. And it's returned 361 terabits. I'm not quite sure why they use bits instead of bytes, but something to keep track of. Compared to Cassini, which is another stellar mission that orbited Saturn for 10 years. So similar time scale in terms of orbits around their planets and their moons, returned an order of magnitude less. And this is, again, a function of distance. Saturn is farther than Mars by a significant amount. The technology available at the time of launch and mission design in terms of the data rates enabled by the antenna processes on the missions. And then, again, for comparison, Magellan is really our primary dedicated Venus mission, on a similar order of magnitude to Cassini, operated for about 5 years around Venus. And the difference there is in the types of data acquired. Magellan mapped the surface of Venus with its radar, 97% of the surface. And so it's a balance between how long you can exist at your planet that you're studying and what your orbits are doing to enable your data collection, when you were launched and what types of technology you have. So again, looking into the future, as we are developing new technologies, that is opening all sorts of doors. And then again, how far are you going away? Because that, at the moment, is the fundamental limitation in our data collection schemes. All right, so to transition a little bit into the nuts and bolts of planetary remote sensing, and some of the concepts that we think of in terms of how are we answering these scientific questions. Most people in the room probably know this, but to set some terms, resolution informally is kind of how much information is available in a bit of data. So in terms of imaging, this is dependent on your field of view of the instrument. You can have an amazing camera, but if you're 135 kilometers away from your target, you're going to have a much more limited surface resolution than if you can get up close and personal to your object of interest. And so your trajectories and your landings are a fundamental limitation on how detailed can you look at your target. And this is, again, I've used the example of the Dawn mission at Ceres here because it had a progressively inbound orbit and had a series of mapping goals. So at each step of the orbit, it mapped the surface of Ceres at increasing resolution. But at the same time, so you can get a global map when you're out at a certain distance. But as you get closer, that means that your orbit is coming in like over the northern hemisphere. And so you get great coverage in the northern hemisphere. The southern hemisphere, you get okay. But again, because your trajectories are being a major controlling factor. This is also, again, using Mars as the example because that's where we have all the data. Being able to scale from the MRO orbital observations down to Curiosity taking a picture of that pebble on the ground, we're looking at an issue of scale and an issue of the level of nuance in the questions that we can ask. Resolution also applies to sort of the spectral domain, so it's not just the imaging, but it also matters, what are the number of channels that you have in your spectrometer, what kind of band passes are in there, and again, what you build and design is controlled by the types of science questions that you are asking. What resolution is required to discriminate between different mineral types? For instance, you want to know what the composition of a surface is made out of. So, you can take a multispectral observation with 8 channels over a wide range and get a nice stick spectra, and that is going to tell you something fundamental. But that's going to be really different than if you have, 435 channels with a 6 nanometer spacing with the CRISM instrument, able to actually discriminate between different mineral species that tell you different things about how water interacted with these rocks a billion years ago, right? The level of nuance is important. And this also, of course, then drives how much data your instrument is required to collect. If you need all 435 bands, it's going to be a lot more than if you only need 8. So to continue sort of the primer in remote sensing, we explore the planets primarily via many different methods of spectroscopy. And if we simplify it all down, basically using the electromagnetic spectrum to look at different length scales through the universe. And again, each of these types of measurements have
different requirements in terms of their channels and resolutions and bandpasses, different physical limitations. So I'm going to step through this and show some basic examples from each type of observation here. So at our very high energy end of things, the gamma and X-rays, again, small length scale. So we're looking at the atoms that have been excited by solar radiation and then reflected back to the instrument. So this is the chemical makeup of Mercury from the MESSENGER mission. And so looking at the difference between what elements are prevalent where tells us fundamental things about the geologic history of a planet. Again, so we're trying to ask, how did Mercury form and why is it in its position in the solar system today? And understanding, like, hey, it's actually got a lot of neutron absorptions. That says something about how much hydrogen, which is sometimes a proxy for hydration. And so, fundamental measures about the planet's composition actually then start telling you a lot about its planetary history. So in particular, this, again, modulated by orbit. So we really only get the northern hemisphere. Southern hemisphere is much less well measured. But, we're getting going there. In the UV, we can start asking questions about atmospheric gases, ices, and organics. So now we're starting to look at atmospheric processes. This is Saturn's rings, as measured by Cassini UVIS. This is also where we can look, are there organics present? The Mars 2020 mission is sending SHERLOC, which is a deep UV Raman spectrometer that is very sensitive to the atomic bonds in organic molecules. So again, looking for what are the fundamental building blocks in our solar system. And again, so a UVIS spectrometer is pretty different from a Raman spectrometer, but both using the same fundamental physics in terms of the ultraviolet sensitive bonds in chemical makeups to start asking these types of questions. My personal favorite, the visible and the near infrared. This is really where, this is where our eyes are sensitive. This is sort of the most natural data sets to be working at because you kind of just look at it. So this is where we get our imaging. And it does also tell us something, again, length scales, about the mineral structures of the materials that you're looking at. So this is a high-rise observation. Instrument on the Mars Reconnaissance Orbiter around Mars that is a spectacular camera, 30 centimeters per pixel, of the Curiosity rover, which is the little tiny dot in that yellow box there. So this is also just sort of an excellent picture. It's studying my field site. And so again, you're able to get a lot of detail with this very high data intense instrument from this resolution. But in the same general wavelength, we can also start looking at the mineralogy of this region. So it's the same picture, more or less, with the spectral data sets from the XRISM instrument, which is another instrument on board MRO, which is looking at the mineralogy of the surface. And in red is mapped the presence of hematite, which is an iron mineral. And that is telling us, hey, water was here. But the type of water, the chemistry of the water, changed pretty dramatically when you go just a few hundred meters uphill. And so it's this merging between, this is at 12 meters per pixel, 30 centimeters per pixel, the rover at the surface, is really allowing us to untangle the geologic history of this specific area in significant detail. And the data volumes and the data collection process for this is relatively significant, but maybe not as large as one would think. To keep stepping, another example through the IR. This is really where we're looking at the aqueous history of planets. So how did water interact with rock? So, again, it's very imaging based, looking at the distributions of different types of minerals that only form in the presence of water on the planet Ceres, based on the absorption features in the spectra obtained. And so again, this is, we're caring about the number of channels here in order to discriminate between mineral species. If you go to a little bit longer wavelengths, rather than 4, talking about 20 or so, you can start looking at the silicate minerals. This is instead of water interacted with rock, this is the fundamental igneous chemistry, the stuff that comes out of volcanoes, the stuff that formed as the primary composition of these planets. And so again, these are telling us about different types of processes. But that means that, hey, it'd be really nice to have this spectrometer all the way out, Stepping up in length scales, out in the microwave, this is where we're working with our radar data. This is where we're starting to look not at necessarily the molecular structures of things, but at the large scale structures, the meter scale structures. So I mentioned the Magellan mission to Venus mapped 97% of the surface of Venus at 2 kilometers per pixel, which is pretty dang good given the pretty intense atmosphere obscuration using radar. And so this is bouncing a signal off of the surface of a planet, measuring the return time back, and you can get topography out of that. On a similar type thing, instead of just looking at the surface shape of a planet, you can also start getting a sense of what's underneath the surface. So the SHARAD instrument is another radar system on board Mars Reconnaissance Orbiter on Mars. And so this is a vertical profile through the northern polar caps of Mars. So, significant stacks of water and carbon dioxide ice. And we can actually pick out the structure in the layering. And then finally, we go out into the radio, and this is where we work in terms of our communications, astronomical observations. This is going to be, I think, the subject of several other talks. So moving on. So what I'm going to spend the last 10 minutes of this talk or so doing are stepping through a couple of type mission examples in terms of, all right, so we've talked about the kinds of data that we are interested in collecting. How are we actually collecting them? So I'm going to use the Mars Reconnaissance Orbiter and the Mars Science Laboratory as sort of case examples, partly because that's what I'm most familiar with. But I think it's also in terms of the types of data being collected, in terms of the volumes and the detailed resolutions. These are both really good case examples for thinking forward into the future. Because if we could have MRO at every planet, that would be amazing. OK. So the Mars Reconnaissance Orbiter, like I said, it's been at Mars for about 13 years. It has a very capable instrument set that really does cover the electromagnetic spectrum, right? So we've got our ground-penetrating radar at SHARAD, and then XRISM, HiRISE, CTX, MARCI are all sort of near-infrared to visible imaging systems that are both looking just at, what is the morphology of the surface, but then also what is that surface made out of in terms of the mineralogy and composition, to be untangling the geologic history of Mars, which is pretty complicated. There was lots of water once on Mars that has shaped the surface in pretty significant ways. And so being able to resolve the morphological features on the meter scale and correlate that with what the minerals in those features are is really important for our geological explorations. So in terms of data collection, the primary science orbit is pretty circular. It processes around the planet with an overall ground track of spacing about 5 kilometers in between. And so you get really solid coverage, especially after 13 years. We have been over the surface of this planet an awful lot of times and can see pretty much everywhere. The instrument platform primarily points straight down. This, again, is improving your resolution if you're minimizing the distance to your targets. It does have the ability to roll up to 30 degrees to point off nadir, to again cover more ground and point at specific targets. Of course, that does mean that there has to be agreement between the instruments in terms of what they are targeting, right? Because certain, if HiRISE and CRISM are going to turn off nadir, Charade isn't going to be operating at that time. And so planning cycles operate on the order of 3 weeks in terms of a human thinking about the types of targets that we want to select, picking out where in the orbits they are going to be achievable, sending a set of instructions up to the spacecraft, and then waiting for those to execute and come back down. And it's a balance between the orbital constraints, the instrument requirements in terms of, each of these instruments have their own scientific investigations to make sure that they are checking off, and collaboration therein to be taking these coordinated observations. And this, I think, is really where the Mars Reconnaissance Orbiter has been a great triumph in a lot of ways, in that the instruments really are designed to be working together. So even though there are limitations in the planning cycles about when instruments can be turned on and off and whatnot, things aren't just able to continually take pictures. We're able to coordinate the observations to, again, cover the electromagnetic spectrum and cover the planet. So the context imager is the big long track there. We have a global coverage of that. Very proud of the Murray Lab here at Caltech. We have it's a queryable mosaic of the entire surface of Mars at 6 meters per pixel. You can do a lot at that resolution. Much less coverage, but much higher spatial resolution is HiRISE. We've only covered about 4% of the planet there, and yet the detail available in those pictures is pretty incredible. And you sort of it would be really nice to have a lot more HiRISE everywhere on the planet. And then CRISM starting to look at the mineralogy. And CRISM has a couple of modes. This targeted mode, very little tiny postage stamps, hasn't covered very much of the planet. But in its mapping mode, where it is at a much lower resolution, has, we know what the mineralogy of Mars at 100 meters per pixel, plus or minus, is. This also highlights another mission constraint in terms of data collection. Curiosity is about here. MRO is a very important relay for Curiosity's data. So Curiosity collects information, sends it up to MRO. So while MRO is talking to Curiosity, it can't do science. So a little bit ironically, right where we've got a very capable asset on the ground, we actually don't have a significant orbital coverage of Gale Crater and the surrounding orbital track, just because of that relay constraint. So sort of a reality to manage when you're doing both science and communications. On that note, switching down into the Mars Science Laboratory, this is a very different type of data collection project. It is much more intensive in terms of the hours that people put into this, because in some ways it is much more dynamic. So we have planning 3 to 5 times a week. So this is humans in the loop looking at, what is the data that we've collected, what are we going to do next, and then how do we execute that, and then assess it. Every Mars sol, so every Martian day, we collect on the order of 850 to 1,300 megabits. It doesn't sound necessarily like a huge amount, but the Mars Opportunity rover, towards the end of its mission, was collecting about 15 bits per day, or megabits, excuse me. So when we're talking about gigs of data, I still get really excited. And so that doesn't include the engineering telemetry data that is also collected about rover health, driving, that kind of thing. So there's a little bit more that comes back as well. And so then the way that we operate with Curiosity is we have direct communication when we are sending instructions, but then to relay data back, Curiosity talks to the rovers, and then the rovers talk to us. And that greatly increases the amount of data that we can return from these missions. And so to step through the collection process, so as a scientist on this mission, this is the level of detail that we work with. So for every day, plus or minus, we don't work weekends anymore, it's great. We have, like, here is where we're at on Mars. What are we gonna do here? Where are we gonna go next? So with the instrument set on Curiosity, a typical day for the rover team would be to look at this overall vista, choose 1 to 5 rock targets. That thing looks weird. What's going on with these layers? Target some regular bedrock. Shoot those with our laser-induced breakdown spectrometer to get our compositions. Choose something pretty flat and right close to the rover to put the arm down for alpha particle X-ray analyses and up-close images. Target overall imaging of the horizon, out to, that's the rim of Gale Crater in the background there. And then decide, like, okay, that in the circle there looks pretty interesting. Maybe we should drive over there next. Balance all of the request constraints. So, how much power do we actually have for the day? Like, how long can the robot be operating for and still come in, meeting its power minimums for the next handover plan? When do we have to, at what time are we uplinking this data set? So what time are we communicating directly to the rover? At what times are the rover talking to the satellite relays? That sets, how much time you actually have to do science. And then fit in all of your science requests. Check, double check, recheck. Make sure you're not going to break the robot. Send it up. It executes on Mars, relays back the data, and then you start the assessment process. And that kind of starts the thing over again. So now we're at that spot that we thought we were going to drive to. What are we going to do here? Repeat the cycle. And so in terms of the post-processing, this really allows us to be very careful in our quality assessment. Did we collect the data that we needed to collect? And is it of good enough quality to actually answer the scientific question that we needed it to? This is also where we're able to calibrate our images, reduce our data sets, sort of repeat the cycle. So hopefully what this does is gives you a little bit of a sense of how scientists are thinking about data collection and data analysis that then informs what we're asking the engineers to, hey, go build this instrument, go send this spacecraft, give us our data back, please. Because I think that is a very necessary collaboration as we are thinking about this. So for today, missions are very carefully designed to collect the very specific data sets that we need to answer the very carefully curated science questions that we have proposed for a mission to go answer. And so we ask for just what we need, not very much more. We definitely want a lot more. So what happens if we're able to flip this paradigm of we no longer just have to collect just that particular picture because we don't have quite enough data to get whatever is over to the left of it. And that, I think, is what we are hoping to really start digging into during this workshop. I will leave my very hand-wavy conclusions up here on the board. And with that, open it up to questions. Thank you very much.